the dual spaces of the vector spaces. And we took up some examples also. More examples and exercises will be given to you as the exercises to be attempted by yourself. And Gyanendra Babu will help you if required, and I also will be available. So the next thing that we want to see is some geometric properties of the vectors, and for that we look for what is called the inner product of the dot product of vectors. Okay, so we recall what we know about the dot product from the school that we have, say for example, three-dimensional vectors. We have two products defined there. One is called vector product, another is called cross product, another is called the dot product. So this is the dot product in which we are interested now. So what does it do is that if there are two vectors, say for example, inner product. So if we have two vectors, let us say VB R2 over R, and this consists of all ordered pairs. So say x1, x2, and xi R. And there the usual notation using the unit vector in the x direction as I and in the y direction say j. The vector ix plus jy here will be denoted just by retaining their coefficients by x comma y, or say x1 comma x2, where x1 x2 both are real numbers. And if you have two vectors, let us say u is okay, and define on V for any two vectors, let us say u as x1, x2, and v as say y1, y2. So u dot v is defined as the x1, x2 plus y1, y2, and this x1, y1 plus x2, y2. And there was also one more thing that we defined this as the dot product. V. The vector. Naturally, one can see the properties of this as follows. So properties of the dot product we can see here. So if you take say u dot u with this, so this is your x1, y1. y1 is also x1, so this is x1 square plus y. This y2 is same as x2, so better write x2 only. So this is your x2 square. Now naturally this is the sum of two squares and this is non-negative. Second thing you can also check with this that when is it 0? So u dot u is 0. U dot u is 0. That happens if x1 square plus x2 square is 0, and since this is the sum of two positive real numbers. Therefore, this to be 0 means each of them has to be 0. So this means x1 square is 0 as well as x2 square is 0. Now in real numbers, if the product is 0, at least one of them is 0. Now both are x1. So this makes that x1 is 0 as well as x2 is 0. That means the ordered pair x1, x2, which is u, is also 0. Conversely, if u, that is x1, x2 is 0, that means by definition each of the coordinates is 0. And if that happens, naturally u dot u, which is x1 square plus x2 square, is equal to 0. So what we can see here is that u dot u is 0 and only if u is 0. You can also see that this is commutative. You take u dot v or you take v dot u, because v dot u will be y1 x1. Real numbers y1 x1 and x1 y1 are same. And so x2 y2 is same as y2 x2. So u dot v is same as v dot u. So this u dot v is same as v dot u. And the other thing that one can also see is, say, have here alpha v, or say w1 v plus w. V plus w is the same as u dot v plus u dot w. So this just you can put in the formula and can verify. This also holds true that u dot v dot w is same as u dot w plus v dot w, and can also check that u dot alpha v is same as alpha So these two can be combined together. So this gives that dot alpha v plus beta w same as alpha u dot v plus beta u dot w. And because of the commutativity, you can also see that, and because of the commutativity, that u dot v is same as v dot u, so you can interchange also, and you can see that this alpha u plus beta v dot w is also same as alpha u dot w plus beta v dot w. So this was the case when we considered v to be r2 over r. And one more thing also we had defined there, that the modulus or absolute value here of this was x1 square plus x2 square root b. So this here makes that this is equal dot u and square root of this. So this is the square root of this. Yes. Now, when we wish to generalize this further, so this we shall be calling the norm of u instead of calling the absolute value of this. So we parts it, yeah, because absolute value may not make much sense when we analyze. And naturally, this called the modulus or absolute value or the length of the vector also can be seen that has the properties that length of or the modulus or absolute value or norm is 0 if this vector itself is 0. Otherwise, this is always non-negative, and it satisfies the triangle inequality. That means norm of u plus norm of v is always greater or equal to norm of u plus v, and so on. So there is one more thing is that the angle between them also could be determined. The angle between them, say theta, then cos theta was u dot v by norm of norm. So some of these are properties we would like to generalize in fact, not just for say R2 to R3, which you can visualize also, or Rn over R, but we would like to see this for a vector space over the field of real numbers or over the field of complex numbers. So, in what we shall be following in inner product spaces would be the vector spaces over the field of real numbers or complex numbers. So it will be understood when somebody says that this is a vector space over and an inner product space over F. So F in that case will be real or complex field. Okay, so let us define the inner product properly. So inner product space. So inner product space. So let V over F be a vector space. F is here R, or as I said, the field of complex numbers. Okay. Now define the inner product of two vectors here. So define now here what is called inner product on V as follows. So the notation instead of writing the dots, and people may prefer to write dot, but we using a bracket, and to distinguish this from an ordered pair, we should be using this as this. So this is a mapping from say V cross V and to F. So it takes say for example an ordered pair UV, and the image we shall be denoting is by U. So U comma V, this inner product, this mapping is called inner product. So this is an element of F. That means is either a real number or is a complex number. So define this with the properties. So the properties as follows. So let us take what properties we needed in R2 over R, and almost all those properties we shall be taking up now. Okay. So let us take this say U plus V and W, this is same as UW plus VW. And second, let us take that this is alpha U V alpha, and this is U. By the way, these two can be combined into one. So these two properties hold if and only if the combined one can be written as alpha U plus beta V comma W, same as alpha U comma W plus beta V comma W. Naturally, you can see that if this holds, then you can put alpha and beta as 1, you get this property 1. And if you put beta as 0, alpha as 1, you get property 2. Conversely, if 1 and 2 hold, then this can be seen that this holds, because if u is a vector, then alpha u is also a vector. Same way, this is beta v is also a vector. So you can call this is new u1, this is new v1. So this is u1 plus v1 comma w. That will be u1 comma w plus v1 comma w. And then put for u1 as alpha u. So that becomes alpha u comma w. So that will become alpha u comma w. And same way, when this is v1 comma w, and for v1 you replace by beta v, then this is beta v comma w. That will be beta and times v comma w. So these two can be combined into one. So either these two or this just one property would suffice. All right. So the other thing is you can see that since what we see, so you can put order is not important. These properties are important. Since u comma v is in f, and f is either real or complex. So if it is real number, then it's of course commutative, as we had seen in case of R2 over R or R3 over R. However, if this field is the field of complex numbers, then u comma v becomes a complex number. So when you interchange u and v, then this is v comma u. So u comma v and v comma u may not be same because it's a complex number. But then what relationship they should have between them is that, so if you have u comma v and you have v comma u, that means you interchange, then this is the complex conjugate. This is the complex conjugate of the complex number v comma u. Now, obviously, if u comma v is real, that means f is real, then both of them will be same, and that means that this is commutative. But in general, for the field of complex numbers, the property is inner product uv is the complex conjugate of the inner product vu. And one more thing that you can see here is the polars. So as we had seen, the modulus or length or the absolute value of the vector. Now here, which we defined as the square root of the dot product. So here we see that if we have u comma u, then in that case u comma u, this u comma u, this is this u comma u is always real, that we can see. But before that, this is 0 if and only if u is 0. So these are the four properties that we see. A norm here or define as the norm of u as the square root of this. In that case, we can also and define the norm of u, the norm or length of u as the norm u as the square root of u dot u, and now inner product. So this is by this symbol. This one. Or norm u square is u inner product with. So this map is called inner product, and the vector space with an inner product is called an inner product space. Okay, now some properties one can see easily of the norm also, if you want to see. Some properties are easy to see are as follows. So, number one, you can see that the norm of alpha u is mod alpha norm of u for every alpha in F. F is R over C, please remember. So this mod alpha is always a real number. The second thing you can see is norm of u is greater than 0, is always greater or equal to 0, is a real number, and this norm of u is 0 if and only if u is 0. And third thing is the norm of u plus v less or equal to norm of u plus norm of. This is called the triangular equilibrium. Called the triangular. And or equal to product of norm and norm. This is called the Cauchy-Schwarz limit. So these properties we would like to, of course, prove. So first of all, you can easily take some examples before that. So some examples before we take up the proofs of properties. One is V R2 over R. We have already seen, and for the x1, x2, xi is in R. The inner product here, I'll define the V2 F is here R. As the vectors u comma v going to u the inner product, and if u is say x1, x2, and this is y1, y2, then this going to be x1, x2, y1, y2. Inner product was defined as, so x1, y1 plus x2, y2. is an inner product. So this, so if this, then this defines an inner product, which we call the dot product also. So V becomes R to R becomes an inner space with respect to this inner product. This can be generalized to as follows. So if you just take V to V, Rn over R, in that case the elements are n tuples. So tuples of the form x1, x2, xn, and each xi is in R. And the inner product is then defined here, V cross V to F, F with here being R. So this U V going to U V, and this becomes x1 y1 plus x2 y2 plus xn yn for every U x1 x2 xn and V y1 y2 y in V. So this can be seen that this also defines an inner product over Rn over R. Next, if the field is complex, in that case also we can generalize. So C2 over the C, if we are taking for example. So in that case, this inner product of U with V will take you to a complex number. So that it satisfies all the properties, you can do like this. So third example could be that you take this, say, C2 over C. So that means here you have ordered pairs Z1, Z2. Each Zi is a complex number. And the inner product here is defined here, V cross V, to say F is here, C. So this is your U, let us say V going to the inner product UV, and this is the inner product of, let us say, Z1, Z2 one vector and say W1, W2 another. So in that case, this will define to be. So this is for all U, let us say 2, and all V, let us say W1, 2 in V. So this is Z1 W1. So this is Z1 W1 bar plus Z2 bar. Now bar denotes the complex numbers. Now this can be extended to your Cn over C. So Cn over C, if you take as V Cn over C, so this will have n tuple here. So the Z1, Z2, and let us say Zn, each Zi is in C, and the inner product here will be a map V cross V to this is F, F is C, and of U cross V going to the inner product U. and this will be as Z1 W1 bar, Z2 W2 bar, and plus more Zn Wn bar for all u of the form Z1, Z2, N, and for all v naturally of W1 and v. So this defines the inner product. All these examples can be combined into just one. So take we say Fn over F. So this is here it consists of let us say n tuples. So this is alpha 1, alpha 2, alpha n. Each alpha I is in F. F is R or C. And the inner product therefore is defined here V cross V to F by UV going to U comma V. And this is here alpha I, beta I, bar, summation I is equal to 1 to n. For every u, the n tuple alpha 1, alpha 2, alpha n, and every v, the n tuple beta 1, beta 2, and this is beta n. So one can verify that for f is R or C, for every positive integer n, this defines an inner product. There are plenty of other examples of inner products. So one can verify all the properties. Now, just a few properties let us take about so what is now we are interested in proving the property about the norms. So the two properties about the norms that we would like to prove would be, one is the triangle inequality, another is Cauchy-Schwarz inequality. The Cauchy-Schwarz inequality, once we prove that, we'll give straight away as an application to the triangle inequality. So Cauchy-Schwarz inequality is the first that we would like to prove. For that, let us do a few things here. So now, what we prove is that let V over F be an inner product space. So is lambda. So let us take V over F be an inner product space. So it goes without mentioning that F is R or C. And alpha beta are the scalars in F. Then what you can see is that the norm of this norm of alpha u beta v square, which is same as inner product of alpha u plus beta v with itself. Alpha u plus beta v is alpha bar 2 comma u plus alpha beta bar 2 comma v plus alpha bar beta v comma u plus beta bar v comma v, which is same as, if you can see, this is mod alpha square cos alpha is a complex number, and norm, this is norm of v square plus alpha beta bar v plus alpha bar beta v comma u plus mod beta square norm of h. You can also see that here these two terms are also interesting, that they are conjugates of each other. But anyway, let us prove this. Proof is simply the application of the property of the inner product spaces. So this alpha u plus beta v, and let us take this is w. So this is same for every u v w. This is alpha u comma w, beta v comma w. This is the property that this is linear in the first coordinate. Now put this w as alpha u plus beta. So this will give us, therefore, so this will give us that your u comma w here is your u comma alpha u plus beta v. And now recall that when we have in the second coordinate the coefficients can use that is conjugate. So this is alpha u plus beta v comma u with the complex conjugate. So this is the conjugate here. So this is linear in the first coordinate. So this is alpha. This is u comma u plus beta v comma u and conjugate. So this is alpha conjugate u comma u. Conjugate plus beta conjugate v comma alpha bar. This is u comma w. That's what we are doing. This u comma w. So this is u comma u. Now recall that u comma u is the norm of u square, and this is a real number, and this always gives you the conjugate is same as itself. So this is u comma u plus beta bar, and this is v comma u. So this is u comma v. So what we have got is that this alpha bar u comma u plus beta bar u comma. Similarly, you can have this v comma w. V comma w. So this v comma w means here you will have alpha bar. So wherever it is v comma w means this is your v comma alpha u plus v. And this is same as alpha bar v comma u plus beta bar v comma. As we had already seen that when the scalars are there in the second coordinate, the conjugates of the coefficients come out. So if you substitute here in the first one, then for u comma w when you substitute, so this is your let us say one. So on substituting in one. So this alpha u plus beta v comma w. So this is alpha is outside. For u comma w we are substituting. So this is alpha alpha bar u comma u plus alpha beta bar u comma v. So the RHS this becomes the right hand side of this becomes your so alpha outside and then this term. So this is alpha alpha bar u comma u plus alpha beta bar u comma v. This is when you substitute for u comma w. When you substitute for v comma w plus beta is outside, v comma w will be alpha bar v comma u plus beta beta bar v comma v. Now this you can see is the same as we desired because beta alpha bar is same as alpha bar beta. So what we get is alpha alpha bar u comma u plus alpha beta bar u comma v plus alpha bar beta v comma u plus beta beta bar u comma v. So this is as desired. So this proves the plan. Now, as a particular case, straight away one can substitute here, say, for example, beta as 0. So what we get is alpha u comma alpha u. So this gives in particular if you put beta as 0 or v as 0, both such situations beta v will be 0. So this will give you norm of alpha u square. This is alpha u, and that will give you that this is same as your alpha alpha bar. So alpha bar u. This is what it is. This is mod alpha square norm of u. And taking the positive square root, you get that norm of alpha u is same as mod of alpha times norm. So like that, simple observations also make. Good. One more thing that we need this lemma we can prove. It's easy to see that if A, B, C are real numbers and A is positive and this quadratic expression ax square plus say bx plus c is always non-negative for all real numbers x in R, then what we can see is that b square is always less or equal to 4ac. The proof is simple. The way you obtain the formula for the roots of the quadratic equation ax square plus bx plus c equal to 0, and that is by making perfect squares. So this ax square plus bx plus c, this can be written as since a is positive, so you can take this. So this is a square x square plus abx plus this is ac, and this can be written as 1 by a, and this ax square plus bx, this can be seen as a x plus b whole square. So this will be ax square plus b square plus twice ab x plus b square. Now what we have here is this is twice abx, but one abx is already here, so this will be minus abx, and plus b square also we have added, so this also will be subtracted. Uh, uh, um, so a square x square plus twice of ax times b by 2, so this will be abx. So these terms will be absorbed here. It will also give you b square by 4, but which is not here. So we have to subtract this b square by 4 plus ac. And this is 1 by a, ax plus b by 2 square. And this is plus, you can see that this is, if you take this is b square this is minus beta compared to minus. So this is here 1 by a, 1 by a, and this is b square by 4 minus c. So this is b square minus 4ac by 4. So this is equal to 1 by a, ax plus b whole square minus 1 by a, and you can see that this is here b square minus 4ac. So this is b square 4ac. This is what it is. Okay. Now this is always non-negative. So this is true for this is always non-negative for all x r. So in particular, when this x is minus of this uh, minus of b by 2a. So when you take x as minus b by 2a, in that case this will be 0, and this is still non-negative. That means this b square minus 4ac should be. So for x as minus of b by 2a. So when you put b by 2a with this, so this will be your minus of b by 2. So in particular, for x as minus b by 2a, this happens implies that b square is less or equal to 4ac. Okay, so this is what we have got. So what we have here, that if ABC are real numbers, A is positive, ax square plus bx plus c plus ax square plus bx plus c is non-negative if and only. So if A, B, C are real numbers, A positive and ax square plus bx plus c is always non-negative for all x in R, then what we have is b square must be less or equal to 4ac. So this is what we shall use here. Now the Cauchy-Schwarz inequality. So what the Cauchy-Schwarz inequality says that let us take V over F, V and inner product space. Then for every vectors U and V in V, what we have modulus of the complex number, which is the inner product, is less or equal to norm mu times norm. So quickly we can prove this. The proof goes as follows. So the case one is when either of the two U or V is 0, U is 0 or V is 0. In that case, then what will happen? Both sides will be 0 because they both, but then U comma V is 0 as well as the product also 0. Because if U is 0, then norm of U is also 0, so the product is 0. Now case 2 we can take here. That U is not 0. U is not 0. But what about the inner product? So we take that the inner product is real and U is not 0. So U is not 0 and the inner product U comma V is real. All right, so in that case, for every real number, ax square plus bx plus c is greater or equal to 0, if a is positive, will imply that b square is less or equal to 4ac. So now let us see here for a real number, let us say x. Now for any real number x here, R, this inner product x u inner product xu with itself xu plus v. This becomes recall that beta is 1, and the lemma that we have just now proved that alpha u plus beta v inner product with itself is alpha alpha bar u comma u plus alpha beta bar u comma v plus alpha bar beta v comma u plus beta beta bar v comma u. So this will give you like here. So this is equal to, so alpha alpha bar, alpha is x here, so x bar, and since x is real, so that will be simply mod of x square. Mod of x square is same as x square, so this is x square. So this is alpha alpha bar u comma u, so this is u comma u plus you will have alpha beta bar u comma v plus alpha bar beta v comma u. Now what we are assuming alpha is here x and is real as well as the inner product is also real. So in that case, alpha and alpha bar are same. That means x and x bar are same, as well as u comma v and u comma v bar, which is v comma u, are also same. So these two can be combined into one. So this will be twice of x, and this will be u comma v plus beta is 1, beta bar v comma v. So this is v comma, which you can write as say u comma u x square plus twice u comma v x plus v comma. So this is of the form ax square plus bx plus c, where a is u comma u and this is norm of u square, and since u is not 0, so this is always greater than 0 since u is not 0 and is real. A, B and C all are real, and this being the inner product with itself, and therefore this also is this. So what we have here is x square plus bx plus c is non-negative, a is positive, a, b, c are real numbers. So this will make that where b is of course twice u comma v and c is v comma v. Okay, so b square is less or equal to 4ac. So this gives that b square is less or equal to 4ac. B square is 4 u comma v, this square is less or equal to 4 times a is u comma u plus product for ac. C is v comma v. Now you can divide by 4 both sides, so what you get here is that this is u comma v square is less or equal to u comma u into v comma v. Now u comma v is a real number and it's a square, so this is positive. So this is same as the square of modulus of v. So this is norm u square, this is norm v square. So what we get here is that this is the square here, u v square is less or equal to norm u square norm v square, and that means this is comma v is less or equal to norm u. So this is the case when u is not 0 and u comma v is a real number. And this is what is the Cauchy-Schwarz inequality in case 2. Now finally case 3 is when we don't have any condition on this. So we can assume that u is not 0 and this inner product is not real. So inner product is not real. So inner product is this u comma v is a complex number, but this is not real. This is not real means it cannot be 0. So this means u comma v cannot be 0. Now this is not a 0, and therefore inverse of this exists. So you can put say alpha. So let us say so the inverse of u comma v exists. This is not 0. This is a complex number, and its inverse exists. So what you can do now here is, so the inner product of u by this inverse of this. So this is u v or comma v. Now this is a scalar. So this is 1 by this scalar. So this is the scalar. So this comes out with the is in the first coordinate. So it comes out to be this. So this is of the form that alpha u comma v. So this is alpha. Alpha is here 1 by u comma v and u comma v. And this is definitely is 1. And now this is real. And 1 is real. So what we have got is that u by u comma v is 1 and is real. Is real means then by part 2, we had proved already for, and the inner product is real. In that case, what does this part 2 says? This 1, which is the inner product of u by u comma v, this is alpha v. Now this has to be less or equal to, so the absolute value of this is also 1, is less or equal to the product of their norms. So this is the norm of u by u comma v times norm of v. Now this is 2 alpha, and therefore this is same as 1 by modulus of u comma v times norm of u times norm of v. Norm of v. You can now multiply by this absolute value of the inner product on both sides. So what we get is, this is modulus of u comma v less or equal to norm of u times norm of v. And that's what is the Cauchy-Schwarz inequality, and this is what we wanted to prove. So what we have proved is the Cauchy-Schwarz inequality. So we shall start from here in the next day. So thank you very much for your kind attention.
Thank you, sir.